All right, Wednesday. Let's take a look. Do a few of these and see what we got. Turn on the visualizer. What's he talking about over there out loud? Can you hear him? What is it? Can't tell what it is. In my high school, we would not have had that wall back there, and you could have almost looked into another entire classroom. And anybody walking in the hallway, like they basically were walking right by a classroom of students just watching them. It was the weirdest thing. They called it open classrooms, and I have no clue. It was something during the '80s, but yeah, if you were a student that couldn't pay attention, basically you would be in history class looking over at the German class and just watching that the whole time, right? It was ridiculous. I think they've since put walls in and changed it. I think that was some type of experimental thing. All right. So yesterday we talked about Q. We said how the last thing we talked about was how this is 5. So the actual product to reactant ratio was 5-1 here. 5 products to 1 reactant. It needs to be 150. So that
You
means
aren't sharing your screen.
what is it?
You aren't sharing your screen.
Oh, my mojo's gone. Who was that? Was that who told me that?
Lily.
Lily, are you trying to be student of the month?
Maybe, I don't know.
Maybe. All right. Let me share that real quick. Sorry about that. So blah 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 what I just said. And let's take a look here. Yesterday, the last problem, thank you, Lily. The last thing we did was we talked about how this was a 5-1 ratio. We know that at equilibrium, it actually should be 150-1. So we only have a 5 product to 1 reactant ratio. We need to be up to 150-1. So that means that the forward reaction will be faster at point Q than the reverse reaction. So basically, we will be going forward, making more products, using up reactants until we get to that 150 to 1. Let's try this next one down here. So consider the reversible reaction, nitrogen plus oxygen yields dinitrogen tetroxide. If we have the following concentrations, so let's go ahead and put it, check our states, all gases. So we're going to have the concentration of N2O4 on top, products over reactants, O2. Again, you have to look at these as tiny elementary reactions. So whatever the coefficient is here, elementary rate laws, right? Whatever the coefficient is there, that is going to be the power we take that to. They then say, okay, if we have this, is the system at equilibrium? So again, Q and K are solved the same way. We just call it Q because it's not necessarily at equilibrium. Q stands for the quotient. So if we take a look, we're going to take the N2O4, which is the 0.00050. We're going to divide that by 0.015 and 0.020 square. Don't think my watch can do that. So I'm going to go ahead and pop this in here. 0.00050 divided by 0.015 divided by 0.020 square. $83.3 is what we get for Q. If we look, we're probably dealing with 2 significant digits. So 83. So Q is close enough to K. We would probably assume that this system is equilibrium. Under part C, problem 1, you calculated Q equals 5. You concluded that the reaction is not at equilibrium because 5 does not equal 150. Which direction is favored until equilibrium is reached? Well, we said we got to make more product. The way we make more product is we use up reactant and we go forward. All right. I think I am going to change what the calendar for this week. I'm going to have to. Okay. All right. This is all the same stuff. Let's pick a problem at random. 3 has too many parts, so we're not picking 3. 4 is too easy. Let's just do one of these. All right. So if we take a look, gas. Again, if we have gases, we can go with concentration, which is moles per liter, or we can go with partial pressure for this. I think next week we'll teach you how to go between the two, but this one deals with concentrations. As we can see, it is molarity. Following reaction reaches equilibrium. Calculate the equilibrium constant in case of a Q if the final mixture contains blah, blah, and blah. So again, who goes on top? Products. Again, I'm wondering, are we done with this? Is this too easy? Should we move forward? Yeah? Yeah, all right. So we'll do this and then we'll move forward. All right, so if the final mixture contains 0.18 H2S, that's going on bottom, and 0.014 of H2, and 0.035 of the sulfur. 0.035 times 0.014 square divided by 0.18 square. Boom. At equilibrium, who is favored, products or reactants? Reactants. This number is way less than 1, so the reactants are favored at equilibrium. All right. Cool. Going away from the thing, let's go ahead and talk about Le Chatelier's principle then. So Le Chatelier's principle, Le Chatelier's principle is one of those things that are, you know, for industry, and it's one of those, and war. It's one of those things that basically is like awesome. So if we understand reactions go forward and backwards by incorporating what we call Le Chatelier's principle, we can adjust and make a shift in the reaction rate. So let's say that we want to kill the allies. So our product is chlorine gas, right? We want to make as much chlorine gas that we can. As we make chlorine gas, if we vent off chlorine gas, right? Let's say we have a decent size K. As we vent off chlorine gas, what does that do to the concentration of the products or the ratio of the products to the reactants? If we vent off chlorine gas, the ratio of products to reactants, go ahead.
I just like it keeps it low, so it keeps going to the products.
You got it. So it lowers that ratio. So what does the system do to reach back to equilibrium? It makes more of that awesome chlorine gas that we use to kill the allies, right? This is one of those things, you know, that was used. A man by the name of Fritz Haber. If you've read anything or looked at anything, the Haber process. I can't remember the name of the other scientist because I don't know, Haber may have killed him. Like Haber was, he's one of the craziest German scientists, World War I and World War II. I don't think he killed him. I just made that up because I don't remember his name. But the Haber process is basically the ability of making ammonia out of hydrogen and nitrogen. The biggest component of this atmosphere that we have is nitrogen at over 70%. Nitrogen, as we know, is a huge thing that we need for crops to grow. Well, Germany, with its small land size, its small land area, overpopulation, couldn't keep up the demand of food to people ratio. Haber saw this, and he's like, "We've got to do something for almighty Germany," type of thing. Using Lechatlier's principle, he found a way. I mean, it takes energy to break a triple nitrogen bond, right? Takes energy. So the problem with this also is that it is an exothermic reaction. So if you add heat into there, right, it's going in the reverse reaction method, right? Because it's exothermic, if we pull heat out, it would be different. But it takes energy to break that triple bond. So what he did was he affected the pressure. And that actually is something that allowed him to force that reaction forward to make ammonia, which then could be used to make ammonium nitrate, awesome explosive, and as well as an awesome fertilizer for crops, right? But yeah, this process allows you to kind of dictate or manipulate a chemical reaction to make what you want. So a system reaches equilibrium. We do something to it to, in effect, stress it or change where it is. So we're putting it from K to a Q of some kind. The system then will react to get back to K. And then, we'll see, it's going to make either more product or more reactant. So all we're doing here is we're using, factors that change the K to a Q. And then basically it affects one rate versus the other. It increases the forward reaction, decreases the reverse reaction. So anytime you add something, if we add reactant, that's going to increase the forward reaction. If we add product, that increases the reverse reaction. This makes sense if we look at it as the collision theory problem, right? If we add more reactants are going to collide, forming more products. If we add more products, same thing. So adding or increasing the amount of the reactant, adding or increasing the amount of product. Oh, I guess I'm supposed to write something over here. So adding or increasing the amount of the reactant increases forward rate. Increases the rate of the forward reaction. Okay, pull that stupid picture out there. Can I pull this stupid picture off here? Increasing the amount of product. Well, we have more collisions. In this case, we just have more product, so the higher concentration is going to cause it to break down faster. So adding amount of product increases the rate of the reverse reaction. I don't know how to abbreviate reverse. Is there abbreviation for reverse, Hayden?
You could make one, I guess.
I like your attitude. Removing the amount of reactants. If we take out nitrogen or hydrogen in this case, Actually, this is the Haber equation. That's funny. If we take out nitrogen or hydrogen, what does the system have to do? Yeah, it's going to make more because now when we take that out, our ratio is still screwed up, right? If this were, a 5-to-1, we start taking out this. Now we don't have 5-to-1 anymore. So what happens is a reverse reaction is favored. Does anybody have one yet? Or am I just going to keep writing reverse all day like a fool?
RVS.
All right, I like it. Reverse reaction is favored. Or if I kept with the same way I did this, increasing the rate of the reverse reaction. That's kind of the funny thing about this. If you do reading or watch any tutorials or anything on this, you're going to see people say increasing the rate of the reverse reaction. You're going to see people saying reverse reaction is favored. And you're going to see people saying, well, we're going to shift left. Basically, we're going to shift to the side of the reverse reaction. All of these mean the same thing. Removing the product, well, we take out product. We're no longer at that 5-to-1 ratio. We're less than that, so the system needs to make more product. Yeah, we can just keep with the trend of saying it so many different ways. Makes more product. Or forward reaction favored, shift right, blah, blah. Example exercise. So here we have ammonia plus oxygen yields nitrogen monoxide and water. So predict which reaction will be favored, forward, reverse, or neither, when the following changes are made. We add NO. RF. Let's just do that, Hayden. So much less writing. RF. Adding more of this. We pump in this. We increase this. Not everybody at once. I can't hear you, home players. What is it? Adding more NO. We've got more collisions now with NO and H2O. It's going to favor the reverse reaction. Adding more O2. We've got more O2, more collisions, forward. Pulling out NH3. So we take this stuff out. Now our K ratio is not the same. We need to make more of the NH3 to get that ratio back. What makes more NH3? The reverse reaction. Take out H2O. Well, now we're taking out this stuff. We need to increase the concentration of this. What increases the concentration of H2O? Forward reaction. I had this student, I don't know, I used to do these extra credit videos. I haven't done them in a while, but the student did some weird thing like where she like made a teapot and basically she moved her body or like, if we take away this, the system needs to make more of this. Like she had like a dance for it. Yeah, it was silly because in my mind I'm sitting there going, you take this away, they have to make more, right? But like she had a dance with tipping and stuff like that. So whatever gets you there, right? Whatever gets you there. But if you take away something, let's say you run out of toilet paper, you need to replenish it, right? So whatever makes more of whatever you took away out. If you have excess bananas, it's time to make banana bread, right? Use that up. If you have excess of something, use it up. Whatever reaction uses that up, that's the one that's favored. All right. I'm going to put a little bit of a delta H in here for no reason, it looks like, because we're still just doing the same thing. So if you have extra C2H4Br2, you got extra this. We got to use it up. What uses this up? Forward reaction. If we take out C2H4, we need to replenish the supply of C2H4. No matter how you think of it, if you sit there and you think of that mathematic ratio or whatever you do, apparently we need more of this if we remove it. The only thing that makes more of that is the forward reaction.
Is there any case in which neither will be the answer?
Yeah, but we're not there yet. All we're doing is removing and adding things. There's no case in that where neither could be the answer, unless the thing that you were removing or adding were a catalyst or something like that. If you're at equilibrium and you remove a catalyst, nothing's going to happen, right? You're going to stay at equilibrium. If you're at equilibrium and you add more catalyst, nothing's going to happen because you're already at equilibrium. Does that make sense? But yeah, removing product or reactant or adding product or reactant will have some factor because it's that K ratio. All right. Pressure. So if we take a look at this, we know that any mole, no matter what the gas is, at STP, 1 mole of any gas takes up how much space? 22.4 liters. So we know that here we have 1 mole and here we have 3 moles. And here we have 2 moles. So the total number of moles on our reactant side is 4. Total number of moles on our product side is 2. This one, if we were to look at this in the same amount of space, the pressure of the reactants would be higher if the volume, maintains the same. And all we had were reactants, the pressure would be twice as much. Half as much here. Keep in mind that's if we have only all reactants or only all products. So if we look at this as having it at equilibrium, well, let's take a look. When discussing pressure, only consider those reactants and products that are
Gas.
Thank you. Right? Rules. Increasing the pressure, or what increases pressure? Decrease volume. What did she say? Oh. Decreasing pressure, increasing volume. I don't have to write that. Something gets bigger, we've got more space, the particles are not colliding as much, therefore the pressure is lower. Something gets smaller, particles are closer together, they're colliding with each other, they're colliding with the wall more often, increasing pressure. Predict which reaction will be favored, forward, reverse, or neither when the following changes are made. The volume of the container is decreased. Well, if we take a look here, we have 9 moles, and here we have 10 moles. So the volume of the container is decreased. This will favor the side with the least moles. Right? If you were in an elevator and all of a sudden the wall started closing in and you had the ability to just absorb people, like, that's what's going to happen, right? Because the less moles, the less space that needs to be taken up. Which side has less moles? You guys are awesome. And that's the cool thing about chemistry. I think they just said like 2 totally different things, but they meant the same thing. I would say the reactant side, somebody in here said the left side. What did you say? Oh, that's wrong, actually, isn't it? Yeah. So if we take a look, the reactants have the least moles. The left side has the least moles. And if we were to favor something to make the left side or the reactants, which reaction makes that? The reverse reaction. So predict the reaction that will be favored. it is the reverse reaction because it makes the least amount of moles. And the least amount of moles takes up the least amount of space. If you just decrease the size of your container, you don't have as much space as you used to anymore. The pressure of the container is increased. Same thing, right? Reverse reaction. The pressure of the container is increased. Well, what is the trick in this one? Louder? Close. You fell for the trick, though. Yeah. There's a solid. It was Hayden that said that we only consider reactants or products that are gases, right? So we've got that trick solid in there, so don't pay attention to that. That puts us 4 here and 3 here. Pressure of the container is increased. That puts the squeeze on it, so we want the side with the least moles forward. Volume of the container is increased. That relieves squeeze. So we can favor the reverse. Same thing. Actually, this has a bunch of them. What will happen if to the NH3 if the pressure goes up? This is another way to ask these questions. Instead of saying what's favored, forward or reverse, they say, hey, okay, let's take a look at one specific thing. In this case, NH3. That could be true because, I mean, if you were making chlorine gas to kill your enemies, you may not care about anything in this equation except for the chlorine gas. You're like, just make me as much chlorine gas as you can, right? If you've ever read All's Quiet on the Western Front, chlorine gas is rather heavy in World War I, even in the World War II. What's the major fighting style at the front? Trench warfare. Chlorine gas was your friend to kill your enemies because it's so heavy that it would drip down into the trenches. So if we take a look here, our focus is not chlorine gas this time, it is ammonia. So what will happen to ammonia if pressure goes up? We need to look at this. We have 9 moles on this side, 10 moles on this side. Pressure goes up, that puts the squeeze on. Are we going to make more ammonia or less ammonia? More. Concentration of ammonia goes up because we favor the reverse reaction because it has the least amount of moles. And when the pressure goes up, the squeeze is on, you're going to make the least amount of moles. That system is going to favor making the least amount of moles. Because the least amount of moles take up less space. What will happen to the NO2 if the volume goes down? What the volume goes down, that's the same thing as the pressure going up. What will happen to the NO on the side that has 10 moles? It will decrease. What will happen to the O2 if the NH3 goes up? Well, if we have an increase of NH3, what will happen to the O2? Well, if we add NH3, then that NH3 is going to collide more with O2, causing the O2 to go down. Right? Now, if this is kind of a weird reading, I'm thinking that they changed the concentration of NH3. Now, if it was something that forced the reaction this way that made the NH3 go up, then the O2 obviously would go up as well. But it looks like they just focused on the NH3. They're like, let's do something to the NH3 only. That's going to cause it to react faster with the O2. What will happen to the H2O if the temperature goes up? Anybody? We got to know if this is exothermic or endothermic, don't we? Yeah. So we don't know yet. So let's take a look at the effect of changing the temperature. In order to correctly determine how temperature will affect an equilibrium system, we must know whether it is exothermic or endothermic. Exothermic may be written as blah, 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 plus heat is a product. Or they could give you delta H equals negative something. Yeah, that's good enough. So if we take a look and we imagine heat as a product, if we pull heat out, the system will make more heat. Just as if we were to pull NH3 out, the system will make more NH3. If we put heat in, the system will use up that heat, right? So it's quite easy. Increasing the temperature is like adding more heat. So the system does something to alleviate that extra heat. What alleviates that extra heat? The reverse reaction. I don't know. What do you say, RVS? I don't like it.
I think it should be REV.
Rev.
I think that makes more sense.
All right. I'm going to put a poll up on the. I like this one better. You're fired, Monk. Yeah, you are going for student of the month. So if we take a look, decreasing the temperature of the exothermic system is like pulling it out, grabbing it and pulling it out. What does the system do? Needs to make more heat. What makes more heat? Forward. Yeah, that's just so easier. FWD. Endothermic reactions are like blah plus heat yields this. Or delta H is positive, right? Increasing the temperature is like adding more reactant. Adding more reactant makes which reaction go? Forward. Decreasing the temperature is like pulling out reactant. Pulling out reactant, system says, oh no, we got to get to equilibrium. We need more reactant. So reverse. Questions there? Describe how the system will shift when the system is heated. Is this endothermic or exothermic? Exothermic. How are you guys on that? Like, remember, here's Mr. Jackson with money. Here's Mr. Jackson and money. Know the difference? We don't see heat on this side because it's within the particles, just like the money is in the pocket here. Mr. Jackson has been separated with the money or lost the money. Yeah, right? Now very sad, but that's what this is, right? What's the opposite of this reaction? Well, Mr. Jackson and money, he sees the money, puts the money in his pocket. He's absorbed it, right? This would be endothermic, that is exothermic. Describe how the system will shift. I don't like the shift thing, but yeah, you might have to know it. If they say shift left or shift right or whatever, it's going to be there. Describe how the system will shift when the system is heated. We add heat. I like favoring the reverse reaction better. They may say shifts left. Right? And the system is cooled like we're pulling it out. Favors forward. Yeah, let's take a look at this. Let's see if we can get just get you guys enough practice for Friday. Each of the following equilibrium systems determine whether forward or reverse reaction or neither is favored. Back to the neither thing. Back to the neither thing. Back to the neither thing. I don't know if I had an example and I just didn't do it. Who asked that? Was it Creedon? Back to the neither thing. Imagine we had both the same number of moles of gases on each side. Any change in volume or any change in pressure would do what to the system? If we had 5 moles on reactants and 5 moles on products, there would be no change, right? So that's another time that you would have neither there. So this right here is exactly like we've been doing. This right here is a little bit different. So you have this reaction. They tell you it's exothermic. So which side are we writing heats on? Products or reactants? Products. So they're going to add, in this case, NH3. That's adding reactant. So what happens here? The concentration of O2 goes up or down? Down, because now the excess NH3 is colliding with the O2, bringing it down. What happens to the concentration of the products with added NH3? More collisions of O2, that goes up, right? Now we remove NH3. What does the system do? We take out NH3. The system has to make more NH3. How does the system make more NH3? Reverse reaction. What does the reverse reaction do? It increases O2, but decreases the products, right? Yeah, let's focus. Try some of these tonight on page 11. Then we'll go through 12 and 13. And then tomorrow, and then maybe take a look at 14. And then Friday, just plan on working through 14 or whatever. Questions? Well, that's all the mojo I've got. I've got the Cornelius effect. If you have questions, by all means, stick around. Otherwise, get out of here. Have a great day, guys. This class leaves faster than any of my other classes. Hayden, are you okay?
Yes, I'm good.
Good, good. Have a great day, sir.
Thanks.
I can't give Lily. Oh, I should stop the recording.